Okay, welcome to the first lesson on rational functions. And we're deviating from section 3.4 a little because I don't feel that the book teaches you any calculus, but a lot of these ideas are calculus ideas. Okay, so the first thing is we're just going to put our new word of the day on here, rational function. So rational function is a function of the form p of x over q of x, where p and q are polynomial functions, and the q of x there is not the zero function. We don't want it to divide by zero, so we definitely don't want the bottom to be zero. Okay, some examples of rational functions are anything that looks like a ratio. So like x squared plus 2x minus 4 over x minus 3. That is a rational function because it looks like a ratio, top and bottom, right? Okay. The domain is always basically whatever won't let the denominator be zero. So we've seen this before. This is not a new thing. But basically, it's all real numbers for which q of x is not zero. I am not saying the domain is all real numbers. I am saying it is all real numbers for which q of x is not zero. For example, if you were doing a problem like x squared plus 2x minus 6 over x plus 5, negative 5 is forbidden, right? It is not allowed because it makes q of x 0 at the bottom. Okay, so x cannot equal 5 is your domain here. Okay, so this always brings up an interesting question. Some students want to know, what happens if you're dealing with a situation like this? Watch close. And let's say you have x squared minus 2x minus 3 all over x minus 3. And then you suddenly realize that you can factor the top, x minus 3, x plus 1. And then you notice, hey, I can cancel out the x minus 3. Does this mean then that 3 is allowed? Do you understand the question? See, some students cancel that out, and they're like, oh, it's x plus 1. And then I say, what's the domain? They'll say, all real numbers. It's a line. Is it all real numbers? Or is it all real numbers except 3? Yeah, you have to keep the denominators uncanceled when you record your domain. So you have to say that x equals 3 is forbidden. You have to write that down. Then you may cancel it. Okay? So it's very important you understand, for example, down here on this little note, that a graph like x squared minus 1 over x minus 1 and x plus 1 are not equivalent functions. These are not the same thing at all. Because f of x equals x plus 1 is just a line, obviously. It has a slope of 1, and it passes through y equals 1. Right? This is f of x. Slope 1, y-intercept 1. But r of x, even though it simplifies to give us the same expression, watch this. If you factor the top, this cancels out. It does appear to simplify to the same thing, but x equals 1 is forbidden. So r of x has a very slightly different graph. It also passes through 0, 1. It also has a slope 1, but it's got an open point at x equals 1. Why? Because 1 was out of domain. So is it a line? Not really. It's a line with a hole punched in it. Okay? Just like you punch a hole in a piece of paper. Okay, so it's linear looking, but technically it's a rational function. Do you understand that? So don't confuse these two. They're different. Now, if you graph this r of x on your calculator screen, it will not show you the whole. The graphing calculators to date, so far, the ones that have been invented, none of them show holes. And in fact, that, by the way, is the official name of that whole thing. That's a hole. Good name for it, huh? Let's give that a title. That is a hole. So the reason f of x and r of x are different, sorry, I can't write with that green stylus for some reason. The main difference between r of x and f of x is their domains. F of x is an all real numbers sort of thing. R of x, all real numbers except 1. They are technically different functions. All right, let's go to some new symbols. So this can really intimidate students when they see new symbols. Okay? So I'm hoping that that won't intimidate you too much. Having a little trouble with the scrolling here. There we go. You might have seen these symbols before on the whiteboard when you walked in or whatever, left over from the morning calculus class. But listen, when you see a new symbol, that doesn't mean it's hard, right? If I showed you my Chinese name, if I wrote out my Chinese name for you, you'd be like, whoa, that's hard. But if you grew up writing it a million times, it's not hard. See what I'm saying? If I wrote CAT on the board and showed it to a Chinese person who's 3 years old, they'd say, whoa, what's that? Like, I can't even read that. Like, they wouldn't say it in English either. They'd say, wow, what's yeah. Okay? I cannot read it. Well, boy, can't read it. Okay? But if you were Chinese, or if you're American, you would understand it, right? So it's just symbols. It's just notation. Don't be intimidated by it. Now you want to see my Chinese name, right? Yeah. Okay. So here it is. This is my last name. It's Su. Su is how you say it. When we got to Taiwan in 1977, we told them our last name was short, and they said, okay, Su. It's like, all right, we'll be Su. So it's a nice word, actually. It means nice things. But you see what I'm saying? They didn't have a shore in Chinese, so they gave us Su. And then my friend's last name was Stafford, and guess what they called him? Su. So we were both Su. Don't call me Sue, okay? Don't call me Sue. You can call me Mr. Sue if you want. That's my last name. They use that first, right? So they use their last name first. So if your name is, Su Dawei, that means Shore David, not David Shore. Yeah. Sifu? Yeah, by the way, Sifu is supposed to be pronounced Shifu. Yeah. Which, so you're talking about the Kung Fu Panda show? Kung Fu Panda? Sifu, you want to see that movie? Okay. It's supposed to be Shifu. It means master. It can also, I think it can mean servant too. Shifu is like, does anyone know what that word actually means? Anybody? Alright. So I can't remember what Shifu exactly means. But my point is, when you see a symbol, right, and you're intimidated by it, that doesn't mean it's hard. It means you haven't seen it before. Right? Okay. So actually, once I show you what this means, you're going to be like, oh, that's really easy. Okay. So first let's talk about how to pronounce it. Because when you see something, you have to be able to read it also out loud. So we're going to say this together as a class. Okay? So the first one is pronounced the limit as x approaches a from the left of f of x equals b. The next one will be pronounced the limit as x approaches a from the right of f of x equals b. Okay, so for the first one, what it really means is you're dealing with a function, and if you follow its graph towards x equals a, coming from the left side, you'll find yourself arriving at y equals b. Okay, so here's x equals a, and here's y equals b. And so your curve is going like this, towards the point a comma b from the left. So this is the point a comma b, and you're approaching it from the left. Now what we cannot tell from a statement like this is the exact shape of the curve. We don't know if it's like a graph that goes on forever, if it's just a little piece of a piecewise function. We don't know if it's increasing like I drew, or maybe it's supposed to decrease. We cannot tell details, but we do know that there is this point AB, and the graph is coming towards it. Okay? So it could be any number of shapes. We don't know what shape. Also, the point AB doesn't have to be in the first quadrant. I drew it in the first quadrant, but it could be in any quadrant. Okay? All right. But in any case, this is the point AB. AB might be an open point, or it might be a closed point. Limits don't discuss such things. Limits just tell us where we're approaching, not what kind of point we're approaching, but where the destination of the point is that we are approaching. Okay, so the other one, the next one, is the same thing. We're still approaching A, B, C, but we're coming from the right. Why? Because of the little plus right there. So that little superscript on the A that little superscript means you're coming from the right. So actually when you draw it, when you come from the right, you actually are drawing leftward. Isn't that true? Okay. So it could be any number of shapes as long as it's coming in towards the point AB. Is there a left side to this graph? We don't know. We can't tell from this statement. Okay? We just don't know. There might be. There might not. It doesn't matter. The statement's not saying there is or isn't. Okay, also don't draw little arrows on there. You're just supposed to draw a curve. So don't actually put orientation arrows on anything. Okay, what does this next one mean? Notice the only difference between this one and the last two is I did not put on a what? It just says x goes to A. It doesn't say x goes to A from the left or the right. You see that? It just says x goes to A. So if I don't tell you which side to come from, then you have to come from what? Both sides. Okay? So this is called a two-sided limit. It means you're going to, both sides, the curve is on both sides, and it comes in towards the point AB. Okay? All right, so like this. Here's the point AB. Remember, it doesn't have to be in the first quadrant. I'm just doing that for my example. And the graph comes from both sides. So this is called a two-sided limit. If there's no superscript, like a plus or minus, to tell us which side to come from, we have to assume it means both sides. Okay, this is not hard then, right? It's just new notation. I want to say it one more time. We do not know if the point AB is an open point or a closed point. There's no way to tell from these statements. If this point is closed, right, the curves are still arriving at it. If the point is open, the curves are still arriving at it. The limit doesn't state anything about the point. It just states the destination of the curves. Okay? All right. Now let's go to the next one. So the next one's a little different because we're not going towards x equals A anymore. Now we're going to x equals infinity. Oh, by the way, on that last one, I think you guys had an L right there, right? The first three should say B, B, B. Sorry about that. That was a typo. The first three should say B, B, B. Fix that. But the next one's L. I chose L for the letter. Okay, so on this next one, we're not going towards x equals A. We're going towards x equals infinity, which really means we're just going to keep going and going and going and going to the right. Okay, now, does this curve go up, 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 up forever? The answer is no. It's going to approach a maximum value of L. So L might be 10 or 4 or something. The curve is doing one of three things, actually. It's either coming from below and rising towards this, or it's coming from above and it's falling down towards this line, y equals L. Or there's a third case. Maybe the graph crosses once, twice, many times, but it's approaching y equals L in the long run. So this is just a statement, this limit x goes to infinity f of x equals L. It's just saying that the further out you go, the closer the y values get to the number L. So L might be 10 or whatever. So you've probably seen this before. This looks like a horizontal asymptote. You might remember that from your algebra 2 class. This is the definition of horizontal asymptote. It's a line which a curve approaches as you go out to infinity or negative. So this is our next topic there. And we don't know if it's the red curve or the green curve or the blue curve. We cannot tell. We just know the graph approaches y equals L. And the further out you go, the closer the y coordinates are to L. So let's say L is 5. The y coordinates might be 4.8, 4.9, 4.99, 4.99999. And they're just getting closer and closer to 5. Or maybe they're coming from above. 5.1, 5.01, 5.001, 5.0000001. They're getting closer and closer to 5 from above. Or maybe the values are going 5.9, or sorry, 4.9, 5.1. And then 4.99, 5.01. And they're getting closer and closer to 5, kind of surrounding 5, going back and forth and collapsing onto 5. Okay? That would be if L was 5. Again, This line doesn't have to be above the x-axis. It can be on the x-axis. It can be below the x-axis. I just drew it above the x-axis. Okay? The next one is similar, of course, but it's got the negative infinity. So that's not going to the right. That's going to the left, obviously. So you just draw this picture backwards. You've got this line y equals L. The curve is either falling onto it, rising towards it, or wiggling towards it, like that. Okay? But that is the negative infinity direction. Okay, one last note for this page, and then we'll get into some practice of our own drawings. If the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x, then we say that the limit does not exist. Okay? Okay? There are other times when we write the limit does not exist. Also, we'll talk about that later. But this is the first does not exist we have in limits world. Okay? Here's what it means. Let's say that there's a graph, and here's our point A, x equals A, and you're coming from the left, and it looks like it's approaching a comma 1, but if you're coming from the right, the curve appears to be approaching a comma 2. This is an example of a function. It is a function. This is an example of a function where the limit does not exist at 1, or at a. So we're studying x equals a, and we see something interesting. The destination on the left and the destination on the right are different. We can only interpret that to mean there is no common destination. So imagine if I decide I want to go to Starbucks. So I drive to Starbucks. I'm driving there, and my wife calls me. She goes, "Hey, where are you going?" "I'm going to Starbucks." No, I say, "I'm going to the coffee shop." I'll say, "I'm going to the coffee shop." So she thinks I mean the coffee bean. So we have one close to our house. So she's like, "Okay, you're going to the coffee shop." So she drives to coffee bean. So we're both driving to different places, right? So later it's all funny, we're laughing about it. And somebody says, "Hey, where'd you guys go today?" I say, "Well, we didn't go anywhere." But the truth is we both went somewhere, but we didn't go anywhere. See what I'm saying? We did not have a common destination. That's how you can think of the does not exist. The two graphs don't have a destination. They have two different destinations. So this, we would just interpret this. We wouldn't answer 1 and 2. We just say there's no limit. Okay? This is extremely important in calculus. The limits that don't exist. Okay? This is the very first of many types of D&Es. You can write D&E for this. Does not exist. Or you can write non-existent. Okay, not very hard. Remember, when we say one more time, it doesn't matter if this point is filled or perhaps it's the top point that's filled. It can't be both, because then it wouldn't be a function, right? Vertical line test would fail. But it doesn't matter if it's the top one that's filled or the bottom one that's filled, or both of them are empty. Limits don't discuss the type of point. They just discuss destinations. So the limit on the left is 1, the limit on the right is 2, and the limit in general does not exist. Okay. Now we're going to practice drawing our own pictures. I give you a statement, and you have to draw it. Okay? Sketch any curve f of x that has the following feature. Okay, there's a lot of parts to this, so there's a lot of drawing. So I'm going to pause it and let you try to graph A, and then we'll check in to see how you did. Once I get A done, you'll feel a little better about B and so forth. Things change when you get to E, it's a different style, and then things change again when you get to J, it's a different style again. Okay? Okay, so for our first drawing, you're going to want to basically discuss the point 0, 1, because A is 0 and B is 1. Right? So we are interested in that point right here. Okay? The first statement cannot tell you if the point is open or closed. Okay? So this part here in blue is a chapter 3 concept. Well, technically it's a calculus concept. We just know that the graph approaches 0, 1 from both sides. How do I know it's both sides? There was no plus or minus on this. So we've done our best to sketch it. I've drawn it so it goes up and then back down. You can draw it so it goes down and back up. You can draw it all going down. It doesn't matter. You can't tell the shape either. Okay? But the second statement is not a chapter 3 concept. It's a chapter 2 concept. F of 0 equals 1. What does that mean? It means, yeah, f of x actually passes through the point 0, 1. So far we've been drawing f of x. That blue curve is f of x. And now we're saying that f of 0 is 1. So now we are talking about x equals 0. We're filling in this point. So this is a graph of f of x, the blue and red together. Okay? So your final graph looks like this. I would say that f of x is continuous at x equals 0. Would you agree? That just means, remember from the first video of 3.3, it means you can pass right through the point 0, 1 without even lifting your pen. Okay? All right. So these two are the same. They're both 1. That's why it was so smooth and continuous going through. Or continuous, I should say. All right, let's look at the next one. There's a slight hiccup in the graph. Try that one now. Okay, so this is very different for many reasons. First of all, we're no longer studying the point 0, 1. We're studying the point x equals 2. So we're over here at x equals 2. And what we see is that the first statement is telling us to arrive at 2, 3 from both sides. So we will. So let's arrive towards 2, 3 from the left and the right. That's the point 2, 3. But f of x itself, which is my blue curve, does not touch 2, 3. We know that. F of x actually touches the point what? 2, 4. Correct. So the graph is actually like this. This would be like if I drove to Starbucks and my wife drove to Starbucks, but we got there and there was a little sign out on the door that said we've moved 1 block more. Okay? So our limit is 3. We were both driving towards y equals 3. But Starbucks is at 4. Either we didn't know where Starbucks was supposed to be or they moved. Does that make sense? So the limit exists, the limit is 3. The point exists, the limit is 4, but they don't agree. They're not the same number. So we would say that f of x is not continuous. See that? There is a slight hiccup in the graph. If you try to draw this graph, you would have to lift your pen to plot that red point. Okay, so the final graph is the black. Here goes. F of x is not continuous at x equals 2. Question, does anybody know what we call this little hole in the graph right here? A hole. Yes. Good. All right. It's also called a point discontinuity or a removable discontinuity. Let's go to part C. See if you can sketch that one. I'm going to sketch it at the same time. But this just reminds us we don't have to study quadrant 1. Also, we can just make our graphs whatever curve we want. So I'm making like an absolute value curve. But do whatever you want. As long as your two branches approach the point -1, 2. Okay, what am I going to plot for my red dot this time? F of -1 is undefined. So it passes through the point -1, undefined. Yeah, this is where we just wouldn't draw a red dot like we've been doing on the last two. We're not going to draw it because they're trying to tell us not to. That's how they say it. They'll say f of -1 is undefined. In other words, -1 is not in the domain. Why are you drawing there? Don't draw there. Okay, we won't. So we won't draw. Notice this is a little different from the previous picture, but you can still say there's a hole, right? There's a hole. So there's kind of two kinds of holes. There's holes that are not filled because the point is elsewhere, and there are holes that are not filled just because the point doesn't exist anywhere. This would be like if my wife and I drove to Starbucks and it was burned out. going to do part D because it's just a duplicate of part A. It's not exactly the same, but it's too similar to part A. I do want to hit the last 10 problems here. The 5 on the left, E, F, G, H, I, those are all the same style. These are called infinite limits. And then these 5, J, K, L, and N, those are called limits at infinity. It's a little bit different wording there. If you want to write that down, you can. The first 5 on the left are infinite limits, and the ones on the right are called limits at infinity. But they mean different things. Okay, so I'm going to help with E, and you can do the others. The way it's pronounced is the limit as x approaches 3 from the left of f of x equals infinity. So imagine coming towards 3 from the left. Here we go. Coming towards 3, coming towards 3. And then what's my destination? Infinity? Interesting. I guess I'm going to have to go really high up like that. See? So just draw any curve you want. I don't care if there's x-intercept, y-intercept. I don't care about that stuff. Just make it go up as you come towards 3 from the left. Okay? Now, to show you that I'm not actually arriving at 3, I'm going to go ahead and draw a little barrier here. This is called a vertical asymptote. Actually, a vertical asymptote, by definition, involves the word limit. So if you open up a textbook and you try to study asymptotes, it'll talk about limits. And so you wouldn't even understand it until now. Now you're starting to understand this stuff, I hope. Okay, so there's a vertical asymptote of 3 is what's going on here. Is there a graph on the right? We don't know. This won't tell us. Let's look at part F. See if you can draw F. So you should have drawn the curve going from the right, first of all, and it's dropping to negative infinity. So that's what you should have drawn. Again, I don't care about your x-intercepts. You can include some if you like. Try part G. So I drew it where you start on the right side of x equals 3, and it shoots up. Because it says 3 plus, that means on the right side of 3. And infinity is shooting up. How about, the next one. The next two, actually. Notice there's no superscript on that 3 now. What does that imply? What does it tell you? Both sides. So draw a graph that goes up to infinity on both sides of 3. See? So see if you can draw that. So maybe something like this for part H. And this for part I. Make sense? Okay, this is not rocket science, but it's new notation. So it might as well be Greek to you until you know what it means, or Chinese, right? Okay, these ones, when x is going to infinity, means you're going out to x equals a million, billion, trillion, keep going. If x is going to negative infinity, you're going left, 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 negative million, negative billion, negative trillion, keep going, going, going. Okay? In all these cases, the y is going to do something. In the first one, the y is going to go to 4. In the second one, the y is going to go to 10. In the last three, the y is going to become unbounded in one direction or another. So I'm going to draw these graphs quickly because we're running out of time. But the first one, we're going to the right, and everything seems to be getting closer to y equals 4. So it could be rising up towards it, falling down towards it, or wiggling onto it. So the wave is like getting closer, smaller amplitudes, like the wave's shrinking its way onto the line y equals 4. It's almost like y equals 4 is its desired role model. It wants to become a straight line just like y equals 4 is a straight line. So it's just slowly becoming that straight line. This one you're going to the left, and the y value that you're approaching is 10, not 4. So I'll make it dotted again. So this is y equals 10. The curve is either rising towards it, falling onto it, or wiggling its way onto it. The The next three you've actually seen before, just not with this notation. Do you remember on your note cards how I had you write statements like, as x goes to infinity, y goes to infinity? Remember you had to write that on your flashcard on the backside? Your flashcard? Well, guess what? This is the real mathy way to write it. It means the same thing. Your arrow is going up. That's all it means. What shape is it? We don't know. Is it arched up like that? Is it arched down like that? Is it a straight line? We don't know. We just know that the arrow is going up to the right. The next one, the next two are basically arrow down and arrow up on the left. Okay? So you'll be receiving a worksheet for tonight's homework, very different from the book, where you have to practice these skills. Okay, that's it. We'll pick it up tomorrow.